the presenter, it's a gentleman who has spent over 28 years in the oil and gas industry, and he has to his credit a degree in chemical engineering, and also in business administration. He is currently the deputy manager in the Petrochemicals plants. And so, if we're talking petrochemicals and the product here, you can be rest assured that you are listening to an expert in the matter. So I'd like to invite Mr. Muse-Ariyoh to please come forward to this presentation. In 40 minutes, I will spend the next 10 minutes
plant of the NNPC WRPC. The power plant is a value addition plant to the processes of Warri Refining and Petrochemical Company. When you say a value addition plant, that means it is adding value. The reason why is that the feed that we are using in power plant is from the refinery. Of course, that is why it is situated next to each other. The feed comes from the refinery, and normally the oil that will have blended up as fuel oil, we are adding value to it. You are turning it in, you are adding through some processes, you are adding value to it to make it into another product. So that's why we call it the value addition plant. And the power plant actually is one of the two petrochemical plants that we have in the Warri Refining and Petrochemical Company. The second plant there we have is the Petroleum plant. The power plant was commissioned in 1988 by the then military head of state, that was Major General Ibrahim. So the plant has been commissioned and it has been on for many years now. You find out that the power plant was built, like I said, in 1988, and also the capacity of the plant is 18,000 metric tons. It is capable of turning out 18,000 metric tons. And also the simple process that we use is just the partial decomposition of that oil that I just called the decanted oil from the FCC. Partial decompose. So if you let it go into full completion, you have nothing more than carbon dioxide and water. That any hydrocarbon, if you burn it, all you have is carbon dioxide and water. But you don't let the reaction go into completion. You partially decompose it. That means you starve it of some vital components. And what is that vital component? Oxygen. So that's why you see, no, not yet, sorry. That's why you see there the partial decomposition of the decanted oil. And of course, if you are going to have anything, like any feed, you have to treat it. And that's what I'm referring to there, that it is treated. Because in the FCC unit, we have some catalyst that comes along with the decanted oil. We have the specification. If it is over a particular specification, it is not good as a feed oil. So we have to treat it in a separator, an electronic separator. So from there, some of the impurities, the catalyst is removed, and then we have it into our own specification. And of course, like just is written there, the natural gas is also used in the reactor. I'll show you the reactor as you go on gradually, but have it in your mind. There's something called the reactor. The oil is combusted in the reactor, and also there are inputs into the reactor, the air and the oil, and also some other additives that helps us in shaping what we actually want. And of course, after that, the product is cooled, filtered, pulverized. When I say pulverized, there are some carbonaceous break that may be in the product as it is passing through. Carbonaceous, that means it is not well formed. And if it is not well formed, you need something along the process that's going to break it down. And that's why you have to pulverize it. Because if you let it go down into the system, down into the product, our customers who are going to take the product off our hands, it will affect their processes. So that's why you see they are pulverized. That means it is pummel. It is broken down further in case there is anything that is carbonation free there. And then it is converted to pellets. You have some additives that are added, you pelletize it, you dry it, because in the process of pelletizing, you add water, you can add molasses as a binding agent to take it along. And from there, it goes into storage. And the off gas is then incinerated. What I mean by off gas, we'll see as we go along the system. So what are we talking about in carbon black in the first place as we are moving along? Carbon black is elemental carbon. Many of things around here in carbon black. This bag here that we have, part of what is in carbon black. So many things that is in carbon black. So you see that as you go along the next slide. Yes, so like I was putting this slide because before I go there. Carbon black is used in the manufacture of tires. It has been said that tires run on carbon black. Tires run on carbon black. The only thing is that the rubber helps in pulling it together. So one of the major uses of carbon black is in tires. When I say tread and carcass there, is to find out that if you touch the tire, the average tire, one side is soft, the other side is hard. The soft black is an extension that we will have gone into, but we are planning on doing that as we move along. So the tires are made up of two types of carbon black. The hard black, the one that is actually touching the ground, that helps us in having the traction, and also the one that is by the side, which is soft black. And in carbon black also find used in belts. Some of them are black. So there you can't escape carbon black all over. You find it used in many hoses. You find that when you check some vehicles, most vehicles, you find that the color of the hoses are black. That's carbon black. It is part of the pigment that is used in making those hoses. Batteries, gasless, wires, the distribution of wires, printing inks, all over. We have carbon black find used in many things. The printing inks in paint, carbon paper, and also textile. And also, it is used in the food industry. Many people wonder, maybe I let the cat out of the bag when I wrote the tom-tom there. Fine, many people wonder, food industry, why food? But tom-tom, you have some amount of carbon black that is inside the tom-tom that will leave. So it's fine used also in the food industry. The reactors, like I was saying, the carbon black reactors in the reactor is the heart of the whole process. The carbon black is made. Carbon black, any spec that is not obtained in the carbon black in the reactor, it cannot be changed anywhere else in the process. So that means the reactor is the most important piece of equipment, even though we have several equipment in the plant. And it's the heart of the plant, just like it has been stated. There are five tubular shaped reactors that we have in the plant there. It is designed to run 4 at any one time and then 1 as spare. Maybe you could be carrying out maintenance and then in the other particular one. And although we find ourselves using 2, most of this is because of some exigency, but the plant was designed for 4 reactors, and that is the only way we can make 18,000 metric tons per year capacity. And because the reactors are operated at a temperature of between 1,100 and 1,300 degrees centigrade, you can see that is an elevated temperature. Even in the refinery, you don't have such high temperature. But it's only in the petrochemical plant, like in the carbon black plant, you have an elevated temperature of 1,100, 1,300, at times you go into 1,400 degrees centigrade. And because of that, you have to refractory line the reactor. You have to refractory line it because only when it has refractory it can withstand the heat. Average metal will melt at 600 degrees centigrade. So, because of the nature of the elevated temperature in the reactor, we have to refractory line it. And there is also, you will see the composition of the reactor section as we are going along. But you said that at the vaporization section, we have a special section in the reactor. It is in compartments. We have the pre-combustion, we have the combustion, and then we have the cooling section. So part of it is what you have as the vaporization section there. And then the refractory is such that it is made up of many types of materials. It is such that it has to be able to, some of them are precast, and some of them are castables. What do I mean by precast and castables? Precasts they are like bricks. Insulating bricks that have been precast down, and the castable is one that we have to pour in the refractory. So they are all components of what we use in the making of the refractory of the reactor. And the properties are such. Some of the qualities that you expect that refractory will have are refractiveness, thermal shock resistance. Because the refractory that we select for the reactor should have these qualities. If they don't, it will quickly wear away. It must have resistance to thermal shock, it must have scald resistance, it must also have erosion resistance. And in doing all those things, they carefully selected the type of refractory that we use for the reactor. You find out that when you go to for example, the FCC, the catalyst and the refractory they use there for their own reactor section is different from what we use because of our elevated temperatures. And then the liner is backed with high temperature castable refractory, just like I said before, and it's supported by carbon steel structure. And like I said, that this carbon steel structure cannot withstand more than 600 degrees centigrade. Next slide. In continuation of our reactor, because I said that the reactor is the heart of the plant, if you cannot get the specification in the reactor, you cannot correct it at any other point. So that's why we spend a lot of time ensuring that our spec, we get it right in the flow of what we use in the reactor. What are the flows I said earlier on? We use the decanted oil. That is some people call it the oil that we don't use anymore. In the refinery, the bottom of the XCC oil, that's they slop it. They don't have use for it. They will sell it as fuel oil. They're using burning there, they're using firing their heaters. But for it to be able to be used in the petrochemical plant, that is where actually the value addition comes in. And then the part of what we use again in the reactor, like I said earlier on, the air and also the natural gas. Of course, the temperature when we see it at an elevated point of 1,100, 1,200 degrees centigrade, you expect that there will be some combustion there. Yes, we use natural gas and air to first of all have our own elevated temperature. Then we inject the decanted oil into the flame. We don't pump it there, we just inject it into the fine flame, and it has efficient contact with the flame, and that is only when you can control the reaction. If you just pump it in, it will mostly have carbonaceous grease, and it will just sit down and block the whole place. So the reaction, like I said, we are still continuing. It is still part of what we are looking about. The reactor is the heart of the whole process. Reactors are designed to operate in such a manner that the temperature and concentration of active ingredients in the critical forming zones are controlled to produce carbon black with very definite properties at the highest possible yield. What do you mean by that? We are saying that as we are injecting the decanted oil into the high temperature caused by the air and the natural gas, which will get our temperature to 1,100, 1,200 degrees centigrade, we inject the decanted oil. And we also have to inject some other things that will define the character of the carbon black that we want. Later on, we'll get to know the different types of decanted oil that we have. We have different grades. So if you want a particular grade, you have to influence the surface area and the structure of the decanted oil. In our own ordinary eye, if you look at it, you cannot see it, but under microscope, the decanted oil of the carbon black of different grades have different structures, different surface area. And that is what determines what the customer actually wants. That's what determines what they use for the tire, for example, in the tire industry. So the part of the additive we use is potassium nitrate. Potassium nitrate helps us to determine the structure by the concentration of the decanted oil that we inject and also the flow. You either increase or reduce depending on the type of grade that we want. That is for the structure. The surface area is also part of what we check. We will see all these ones later on in the slide. The surface area also determines the kind of grade of black that we produce. If the design quality of the ideal carbon black are not attained in the reactor, it's not possible to produce it any time in the process. Like I said, if you missed it in the reactor, sorry, it just goes as one spec. It goes as another grade, and you have to get it right again. Like I was saying, this is a typical reactor. You can see the section of it. This is what the reactor looks like, but you can see that all these are refractory. Because like I said, they are castables and also they are precast. The reaction state that we have is this state that you are looking at. That is been determined by the castables and the precast. Excuse me. Every other thing here is refractory because the refractory has to be, the reactor has to be refractory lined, and it has to be able to withstand the temperature that we are subjecting it to. If you don't the right quality of refractory, it's just simply going to fail. You will have hot spots, and before you know it, when we say hot spot, that means the refractory has failed at that particular point. That's what we mean by hot spot. So the oil gun is inserted through here. The oil gun, there's an oil gun that is inserted that introduces the oil into the reactor, and that one is inserted right there. And then the additive is the one that comes from that section area. And it has two tangential corners. You have one here that's seat number 4, and also a replica of it on the lower one. Then this one is the lower one, and also the other one that's facing the other side is the higher, is the upper one. They have two tangential corners, radial, so that you have efficient mixing in the reaction zone. So now we have the oil gun that is introducing the oil into the reactor. We have additive that is being passed through that place. Remember we said that we have about 1,100, 1,200 degrees centigrade inside here, and there is a pre-combustion zone where reaction does not take place at all. That is where you just have the high temperature. That is this section here. And then you have the tangential burners. The tangential burner is started from here, and also is started from the other place, number 4, which creates the efficient mixing. And then from there, the reaction travels down. That 8 you see, we have to stop the reaction at a particular time. Like I said, if the reaction goes into completion, you have carbon dioxide and water, and we have not achieved anything. So what we do is that we put a limited amount of air that is required for the hydrocarbon to burn, limited, and also with the limited amount of air that we do to still ensure that we stop the reaction. There's a quench. We have a quench mode to stop the reaction from going to completion. Because if we allow it, the carbon will burn. And the oil will burn and you will not have any carbon. So these are the typical reactors that you have seen there. Next slide, please. Oh, it's working fine. I don't know, it's a bit dark there. Maybe we need to put up this light. 4, 5. And at any point in time, we can do 4, and then one is on standby. We carry out maintenance on it in case there is any need for one of them going down again, we turn the other one on. But we have been using 2 reactors for some time because of some exigency. But this is the average. What you are seeing here for each reactor has an air preheater. It preheats the oil, the air. Okay, there's an oil preheater and also the air preheater. If you preheat, you are increasing your efficiency. That means you use less fuel gas. If you don't preheat, that means you require a larger amount of fuel gas for you to achieve exactly the exact reaction that you actually want. Now those are the 5 reactors, like I said. Each one has its own air preheater. Then based there you have the oil preheater, and along the line there, that is the length of the reactor you are seeing. Only one reactor is not allowing us to see the other one, but they are just packed there. Next slide, please. Pit stop, like I told you, the average pit stop of the decanted oil analysis has been done, it has been carried out, and the pit stop is highly aromatic. Aromatic, that means it's very rich in carbon. So the average decanted oil, the molecular formula, you can see C21, H28 is almost 1 to 1. That means it's very rich, and that is exactly what we are looking for. We want this. This is what we are looking for in the compound plant. In the reactor, we have several reactions that can take place. We have let me start from the bottom. We have carbon. Because somewhere along the line, you check the equation, carbon, you have elemental carbon, which will react with oxygen, and you have this carbon dioxide and water. You have hydrogen too, which will react with oxygen, you have this. Carbon reacts with hydrogen, you have acetylene. All along, you have it like that. You have natural gas methane. You have also the carbon reacting with oxygen, you have carbon monoxide. But the first one, like I checked the molecular formula, when I saw the other one, C20. And I'll go back again. Sorry, the other previous C21 H28. So that is almost 1 to 1. Next slide. So you find out that it is this actual reaction that we are looking for. And this is what we are looking for, carbon. And that is actually the carbon black we are looking for. All other reactions actually take place, but we discourage it. The other reactions take place, but we discourage it. And what promotes this first reaction that we see? Due to the high temperature and limited amount of air, that is oxygen that is in the reaction, the first reaction is promoted. We don't give it enough air for it to go into completion. We just give it limited amount of air. And like, remember I said we also quench it. And when we quench, you stop the reaction. And the first reaction here, what we promote, that's the heat of reaction that you see there, carbon, and then hydrogen. But every other thing here is present in the stream that goes along in the process, but it is not desired. But we require to eat as off gas. And this has to be taken care of somewhere along the line. We incinerate it. But the important one is the number 1 reaction, which we have there. And that is actually what we're interested in. That is what makes it become lactic. And that's what that's where we're in business. We stop the reaction. Next slide, please. Like I'm saying that we have different kinds of grades, different types of heat that we have in the ground black plant. We have the N330, N220, 326, 375. There were times some customers came to meet us. They wanted us to produce N299. Yes, all we have to do is create our processes, change the reaction time, the reaction volume, and part of the additive that we add. Also, with so many variations that we can do, increase severity on our reactor. But we'll get there. We were ready to produce it for them, but they did not sort of come back. But the reactors can be variated to produce any kind of grade in hard black, because we are producing hard black, like I said, in the carbon black. Next slide. Refractory curing. You find out that when the refractory I'm spending a lot of time on the reactor because, like I said, if you don't get it right in the reactor, you can't get it right anywhere. The reactor, when it is freshly lined, we have to cure it. Why do we have to cure it? Because there are pockets of water, moisture all over in the refractory. So we have to cure. When the reactor is freshly relined, the refractory should be carried out before using the refractory curing should be carried out. Curing removes the water moisture in the refractory lining and strengthens the binder. It strengthens the binding that the refractory has. If you don't cure and you want to use it like that, it will just see if the refractory will fail, and you have what we call hotspot. What is hotspot? It tells you that there's a failure there somewhere. In order for it not to fail and also to increase the binders in between the refractory, we cure it. And how do we do the curing? We take the refractory through a heating curve. A heating curve that has been determined by the OEM for us to ensure that the curing takes place. Next slide. Like I was talking about the product specification, the parameters that we check in the carbon black plant, what the customers ask for, because before we can give them the product, we have to give them a certificate. And before we give them a certificate, we have to ensure that the specification is up to what we want. And lab, if our eyes there in production, we don't see anything, but lab takes sample and tell us our product specification in the plant has to fall within this. It is either 330, 220, N326, or N375. In 330, for example, you will see the iodine parameter between 82 plus minus 6. And what is the iodine? Iodine mentions the surface area. Like I said earlier on, the surface area of the carbon black spec. In the iodine number will tell them amount of the surface area that the carbon black spec of it has. DBP, diabatic patalate. Diabatic patalate describes the structure, because the different grades of black have different structures. So for this particular one, you see that for DBP for this one is different from this, is different from 220, 375, and 326. All of them are different. So the diabatic patalate, which is the structure of the carbon black, they are different. And lab takes sample and they will ensure that it is within specification. The moisture content is common to all, 1% maximum. The customer does not want anything higher than 1, and we have to ensure that. The potolometer is the amount of oil, unburnt oil, inside the decanted oil. And we have to, part of the parameter that we check, we have to ensure that it is 85 minimum. And then the pore density, just like density of what each grade is supposed to have. The grades, that's why I said that we treat our feed before we process it in the reactor. If we don't treat our feed and remove impurities, our grades will be high. I can see it is maximum that is written there and not minimum. Maximum. So maximum should not be more than that. But if you don't treat it and the grit is already high in the feed, there's no way you can remove it down the system. And then the fines. Fines is important because when the customer buys our product, you don't want it before they carry it from here to Sapele, half of it has gone into the air. You want to control the amount of fines you have in the product. So it has been determined also that the 7 there is maximum. It should not be more than 7 in the fines. Lab also take those samples for us and let us know the spec. If any of this is out of variation, we carry out our own adjustment based on the flow into the reactor, the parameters that we have in the reactor, be it the oil, the air, the gas, the additive, so many things that we can use in controlling just to get what the customer wants. When we have gotten everything right in the reactor and the flow is moving, like remember I said that there is something like off gas. You know, we all know what the off gas is now. Off gas is anything that is not that elemental carbon that we want. Be it the methane, the hydrogen, the carbon monoxide, and the rest. Everything falls into the back filter. The back filter is the back filter compartment that you are looking at. The back filter, it has 9 compartments. 9 compartments in the sense that each compartment, one of them is always cleaning. There is the filtering section and also the cleaning section. The back filter ensures that there is separation because inside each compartment you have socks. Sorry, I don't have a picture of the socks here. I couldn't lay my hands on it. It is where we achieve our separation mode. It is something similar to the socks we wear. If there is a flow of black into a socks, you imagine that by the time it comes out, some of the particles will be enstrained in the socks, and the one that is gas will go out. That wall of that sock, something is entrained there which we can shake down. When we shake it down into the area we can see very well now, the pulverizer area and also the pneumatic blower area. From here is where we transport it down. So what do we do in the back filter? The back filter is what actually filters our product for us. The off gas that we have in the stream, the elemental carbon that we have in the stream there, it has to be separated. We have to produce the carbon black, but we cannot. We need to separate our product from the undesirable. The undesirable is the off gas, and it's inside this compartment. 9 compartments, all of them, and each compartment has about 499 bags about, and then from there the separation is done. The product now, like I told you, if you imagine a sock, and there is a product that is going through. Normally gas will want to come out from the walls of the socks, but the black will be trapped on the walls of the socks. So all you have to do is shake it down. When the off gas goes out, the black is trapped and it falls down. And by the time it falls down here, it falls on the screw conveyor. There's a screw conveyor here, which transports it to the pneumatic conveyor. What does pneumatic conveyor mean? In the real sense of the name, that it's called pneumatic. That means it flows. There's something that transports it down to our own back end. The back end I'll show you later on, and that back end is somewhere that you are seeing just by the side there. So what we do here, what we want to achieve here, what we actually want to achieve is separation of the black from the off gas, and from there it is transported. It is also there that the pulverization takes place. There's a pulverizer that pulverizes in case that carbonaceous break. It goes, it funnels it and breaks it down. Next slide. The pelletizing and drying. You find out that from the back filter area, we are now going to the pelletizing and drying area, and that is the area you have around here. We have the primary back filter, and there's also a secondary back filter. The secondary back filter does the same thing like the primary back filter also does. It does the separation for us. Only this time around, it does it in a final mode that it shows that the rest of the, because when you say there is a pneumatic, something carries something pneumatic, it's still carried by air, by gas or whatever. You still have to get rid of that and have the elemental carbon that you are looking for. The secondary back filter, and also somewhere around here, in this section, you have the pelletizer and the wet mixer. What does it do? We have powder now, just like dusting powder. You have to have, and it's just like dusting powder. You need to be able to control it. And how do you control it? By the time you wet it. And what do we wet it with? Water and a mixture of molasses. If we use molasses, sometimes you don't use molasses. But by the time you use water and pelletize it, you now break it into pellets. And that's what the section does. You have pelletizer and the wet mixer. And you find out that when you have introduced water, you must remove the water. And that's what this is the dryer. And this grain equipment here is supplying the heat to the dryer. So the water that has been introduced to bind the pellets into position, the water has to be removed from here, and the drying is achieved. By the time you move from the beginning of the dryer down to the end of the dryer, drying will have been achieved. Yes. By the time we leave the secondary back filter and also all this section that we are seeing here, that is dry that we just saw now, we have to transport it up. What you are seeing there is the bucket elevators. Bucket, because it has to be scooped. Scoop it in bucket, the bucket scoop it and transport it up. By now, what we have here, what we have here now are pellets. They are not black anymore. They are pelletized, and you are having pellets moving in the bucket, and it is going to there's a lower bucket elevator, there's an inter elevator that also transports to the upper elevator. And the essence of moving it up is to take it into our storage tanks. Up here, we appreciate that metal may have one way or the other falling to the product. So there's a magnetic drum up there that separates the metal from the carbon black. So the product passes over the magnetic drum before it goes into an elevator there that transports it into the two storage tanks. Inside the two storage tanks is still divided into four, but one particular section in the core is the off-spec tank. Each tank has its own off-spec tank, in case depending on the grade that we are producing. Next slide, please. The carbon black plant, as it is today, what we have as part of our strength is the experienced staff. A lot of our staff over the years have when we started out, we started without the expatriates, and they imparted the knowledge on us. We also tried to impart the knowledge on to other people that are there, and it's going down the line like that. Because without that, without the knowledge being passed along, that plant cannot run. Another strength of this plant that we are talking about is the readily available raw material. We have the content coming from the FCC plant, just our sister company over there. In some other carbon black plants all over the world, they have to transport from long distances their pig, and it costs them a lot of money. But in our own area there, we just, whenever the FCC is on, we have storage tank that we store our own feed into. We have a lot of storage tank that can have a lot of storage for, and also management support. We're having a lot of management support in the running of the plant. There's nothing we can do if management does not give us that support, but we have wonderful support from management. Next slide, please. Our weakness is a lack of critical spares. We are finding out that in the cow black plant, most of our spares, we don't have them. Why? Because paucity of funds. How do I get that message across to us that in the economic downturn is affecting all spheres of the economy, and fund is not easy to come by. But management is struggling with it. They are interfacing with the federal government to ensure that they get the right amount of fund for us to be able to get our spares. And then also, most of our critical spares are not paired. What do I mean by that? When you have a critical equipment that is running and you don't have the B of it, what do I mean by B? They standby. There are some equipment that are on standby, but many of our equipment are not on standby. Like our process air blower is not on standby. Our back filter that I've just shown is only one. It's not there's no spare one of it. Many of our equipments are just single, and all of you can know that when any plant that is on single one leg, for one reason or the other, it trips, the plant goes down. But if there's a standby, if it is paired, you could quickly switch over to the other equipment. All over the world, where many people have traveled, when they say that the equipment are always running, it's running because they have spares. We don't have a spare refinery. So when we want to, they switch over to the other one. But here, most of our equipment are not spare. The next one, the opportunity. What are the opportunities? The cow black plant, we have constraint now. Our major customers used to be Michelin and Dunlop. Michelin and Dunlop are no longer in the country. They packed up and they left the country. Why? Because they had problems with energy, power source. So they found out that in the neighboring countries, Ghana and the rest, they could set up shop and they could do their own business cheaper. So they left the shores of Nigeria. But the cow black plant as it is now, it is the only one south of the Sahara. The chairman of the National Automotive Council was quoted in this day of 18th of January. It was quoted, and I repeat what he said. The Nigeria expended 550 billion on vehicles and related cars and related vehicles last year, 2013. We expended, also 500 billion naira on spare parts. The one that interests me, the one that is coming next. We expended 150 billion on tires. And the cow black plant. This is the one plant that produces the raw material for tires. And the companies that produce the cow black plant, like produce the tires in our industry, they left the shores of Nigeria because of one reason or the other. Even the Lutola tires are not in service anymore. Dunlop and Michelin have left, but we have that opportunity. We can capture the market if only we can get our back straight. We can also, the Nigeria and the rest of Africa can be captured. So for this single plant that the raw material is so cheap for us to get, all we have to do is just get our priorities right, get our equipment, pair the equipment, increase our reliability, we could go to places. Next one, please. Threats. Yes, we have threats. Part of our threat is the occasional discharge into the environment. At times, this is caused by environmental issues. At times we have leakages, occasional leakages, and it pits us against the community. And of course, nobody, if you are seeing what town black is, you don't enjoy it. But important thing that those occasional times that it does, the community don't like it and they are not taking it easy with us. But we are cleaning up our acts and also to be a good corporate responsible organization. Then the lack of adequate funding to procure our spares, like I said earlier on, because of the economic downturn that is happening all over the world, there's positive upon, and we are hoping that management liaison with federal government will give us the funding for us to be able to get our critical spares and also clear our equipment so that we can increase our availability and increase our reliability. Because there is no other one, the Carbon Black plant that is in Nigeria here, this is the one, part of the phase 1 petrochemical plant that we have here. We should keep it running and also keep have the full benefits of what this plant can offer us.